Alright, so today we're going to be talking about regular polygons. We're going to be talking about exterior angles, we're going to be talking about interior angles of these shapes, lots of good stuff. So it's kind of a cool new topic. And as in all new topics in math, we have to start ourselves with a definition. Okay. We need a definition for the word regular polygon. We all know what a polygon is. Poly means many, so it's a many-sided shape. We don't know, however, what regular means. So let's come up with that definition right now. So a polygon is said to be regular if, okay, I'm going to stop right there. Let's see if we can come up with some synonyms for the word regular here and see if we can kind of piece this definition together. So what do you think some synonyms for the word regular mean in this context in particular? Yeah, you way in the back over there. What do you think regular means? Not typical? Yes. I would say not typical, more typical. Yeah, that was good. It's typical, regular, usual. So regular would be typical, classic. How about you in the front? Yeah, talking over here. What do you think regular means? Not weird looking. Yeah, I would say not weird looking. That's actually exactly, yep, not weird looking. Not weird looking. Classic. A classic example. Those are some synonyms of the word regular. So, for instance, if we're thinking about polygon, so let's make our list right here. Not regular. I always think the weirdest sounding triangle is the word scalene. Scalene is where all the side lengths are different. That is not a regular word. It's weird. It's a weird looking triangle too. All the side lengths are different. So an example of a non-regular polygon would be scalene. It looks weird. All the side lengths are different. It's totally out. It's crazy looking. So not regular, that's an example. Regular, however, we're trying to make it look as pristine as possible. Regular. How about a beautiful, equilateral triangle? One that's perfect, one that's classic, one that's typical. That would be an example of a regular polygon. Now, I want to bring attention particularly to thrigons. Three-sided shapes. 1, 2, 3-sided shapes. Triangles. Fancy word for triangle. A triangle, if you have an equilateral triangle, that means automatically, and we proved this before, that triangle is also going to be equiangular. We also showed in class, if you're stuck with some random equiangular triangle over here, that automatically it's going to be equilateral. So when it goes both ways like that, that's an equivalent definition. That's an if, spelled with 2 F's. So right away we know if you're stuck with a triangle, it's equilateral, all its angles are going to be the same. So both scenarios happen. All the side lengths are the same, all the angles are the same. I want to draw attention to this example. So, nope. I wrote nope. This is a weird example right there. It doesn't work with all polygons. For example, foregons, quadrilaterals, for instance. Just because you have a shape with all the angles the same, so right here, all the angles are the same. This is a beautiful rectangle. It does not mean all angles are 90 here. It does not mean, however, that the side lengths are the same. We can declare these to be different. So that side length does not have to be that. Even though all the angles are the same, that would not be regular. It's weird looking. It's an example of a regular, would be where you have a square, a beautiful, perfect shape. Square. Maybe a pentagon. A pentagon is a fancy word for 5. A 5-sided shape is a pentagon. Here we go. you have a pentagon where all the sides are the same. Pentagons need not have all the sides be the same. So if you have a pentagon where all the sides and all our angles are the same, that would be an example of a regular polygon as well. Another example of a not regular polygon would be something that looks like this. Here's this. All the side lengths are the same. Eyeball the angles. That angle right here, that's way over 90. That's like 110. That one's like 10. So those angles aren't equal. So that would not be regular. That's bad. So it's not regular. It's over here. So here's our line. Okay. So we talked about some examples here. We still have to come up with a definition. A polygon is said to be regular if all its angles, in fact, what are these? Are these on the interior or exterior of our shape? They're all on our interior. So if all interior angles, and we need that, and both have to be happening, all angles are the same, and side lengths are the same. All interior angles and side lengths are the same or equal. All right, equal symbol right there. All of those are equal, then you're good. So it's regular. So that's what regular means. Okay, so I would maybe pause the video, write that down. We're going to be talking about something new now, okay? That's what a regular polygon is. Now I'm wanting to get into angles. These shapes. And I need you all to note something. Here's a note. An n-gon always has n sides or edges, n vertices or points, and n interior angles. All of those facts are important to understand, and it might seem automatic. The reason why is it's an induction proof. It's kind of complicated, but all right. And interior angles, but that's a side note. Okay. So an n-gon has n sides, n vertices. A vertex is a fancy word for a point. Fancy point. It's a fancy word for a point. And n interior angles. Here's an example of a three-gon. It is a three-sided shape. 1, 2, 3. It's got 3 sides. Notice how many vertices are here. So vertex is a point. It's where it's jagged looking. So we see right here there are 3 vertices here as well. It's where 3 vertices. Okay. And then, of course, the number of vertices is equal to the number of interior angles here as well. But that's going to be important to realize that, because that also works, with a four-gon. You have 1, 2, 3, 4. 4 sides. You know that you see 1, 2, 3, 4 vertices, points. It's the same thing, and it works for any polygon, any n-gon. All right. So that's that note. I want to draw emphasis to that. Now we can get into, finally, interior and exterior angles with these. I might write that down. Again, pause the video right now. I would suggest getting into something else, something better, something cooler. Now, we're talking about regular polygons. Regular polygons have the same, all of the interior angles are the same. And I don't want to just say regular here, it should be automatic that you think the word regular. But this theorem is actually, it's a bigger theorem than just in context of regular polygons. It's a bigger theorem than that. And I'm going to write the full thing on the board. But it's emphasizing, we're talking about regular polygons, so it should be kind of automatic here. So theorem. An n-gon, an n-sided polygon. An n-gon with all interior angles with the same measure are equal to n minus 2 times 180. Okay, what is that formula again? Wait 1 second. I'm not done writing this. Yeah, this is the formula for here. This is the sum of degrees formula. Sum of degrees formula is right there. Okay. N minus 2 times 180. And then, so, for instance, if we have, everyone knows what the sum of interior angles of a triangle is. It's 180. Here, so if it would be 3 minus 2, we're going 3 minus 2 is 1 times 180, so it's 180. We're wanting a particular angle here. So we're not looking at the sum. We're talking about 1. So what we have to do is, we're going to take 180 and divide it by 3. In this case, n would be 3, so we're going to take that and divide it by n. And in fact, that holds true for any n-gon, where all of the interior angles have the same measure. Okay, so that's what the formula is for detecting what that interior angle of a polygon, of a regular polygon would be. All right. Now, I want to provide a proof of this. But before I get into the proof of it, I'm going to come up with an example, and then we're going to kind of work from there, okay? Example. Okay. Everyone knows that, and again, if you have a triangle, okay. An n-gon, so this is a 3-gon, with all interior angles with the same measure. So if this angle was x, all of the interior angles have the same measure. So this angle right here must also be x. And then, here, I don't like that x. Sorry. So this angle was x. This angle right here would be x. And then this angle, by default, would also be x, because they're all equal here. Now, if we're wanting to figure out what x would be, we know we just take x plus x plus x must equal 180. But in context to, stuff that's larger than this for the number of sides, we need this to look more like this. So it's n. Here we see there are 1, 2, 3 sides. So the sum of degrees formula for a triangle would be n minus 2 times 180. So we're going 1, 2, 3 minus 2 times 180. So all of the interior angles add up to n, 1, 2, 3, minus 2 times 180. That's using the sum of degrees formula right here. Now I'm showing you where this n comes from down below. It's a very good combinatoric problem to just see. So we're wanting to solve for x here, so we write 3x, because we count 1, 2, 3 of these things, is equal to 3 minus 2 times 180. And I'm going to leave it like that. I'm not going to just write 1 here. I'm going to leave it like that. In other words, x is going to equal to 3 minus 2 times 180 degrees. And I'm going to divide that number by 3 on both sides. Notice now, so we can kind of intuitively, reason it with it here, it looks just like that formula right there. You see it's n minus 2 times 180 divided by n. The number of angles, the number of interior angles here. Okay, so that's an example for it. And now we're going to prove it. Okay, it's a good proof to see. All right, let's do this. All right, I'm going to erase this example. It's the same thing. We just need to write this a little differently. A lot of dots are going to go here. It's a good proof to see. It's awesome. All right, proof. An n-gon. So right here, looks like this. And honestly, I'd write this. An n-gon looks like this. This is a proof for it. It would be something that looks, okay, it goes, there's one side length, here's 2, and then we have some other side lengths here, and then it comes back around on itself. So we're going 1, 2, 3, 4, 5, 6, 7, 8, 9, n. It ends on n. We count the number of sides, so it looks like that. Now, we know that here, all of the interior angles are going to be the same. So we call this x. This would also be x. This would also be x. This would be x. This would be x. So they'd all be x's there. Now, we know, we see n sides. How many x's are we going to have here? Remember, an n-gon has with so if you have 1, 2, 3 n sides, you know automatically you're going to have n vertices. So that means you're going to have n angles here. So you're going to have n many of these x's to consider. So if we're going to add up all the x's together, it's going to look like this. X plus dot 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 plus x, and there's going to be n many of these. And that is going to equal, and we're going to use our sum of degrees formula right here. So the sum of degrees formula, because we're adding all those x's, it should also equal to this. So it's n minus 2 times 180. Now, that means, since we have n many x's to consider here, what we can do is we can actually do this. This is kind of cool. Check this part out. We can write this number as 1 plus dot 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 plus 1, and then factor out our x to the right over here. We can bring out that x. You know, we're just using the distributive property here. So we have n many of these 1's. And that is going to equal to n minus 2 times 180. Now, everyone knows if you take a number like 1 and you keep adding it n many times, that number is going to be n at the end of the day. So right here, if we're going 1 plus 1 plus 1 plus 1 n many times, that number is going to be n. So n times x is equal to n minus 2 times 180. Actually, okay. I'm going to pause the video. I'm going to continue right here. So I would write this down here. I'm going to erase the theorem and I'm going to just keep going with it, okay? Sure. So I would write that down right now. All right, so I'm going to erase. I'm going to keep going. Imagine you keep on going here. So I'm just running out of room here. So I'm going to go erasing this. All right. So we were left off here. This number is n, and x is equal to n minus 2 times 180. Okay, so going from here to here. I'm jumping from there to there. All right, I'm going to erase it. I'm going to keep going. Okay, so just the next sentence. So the measure of any angle x would be n minus 2 times 180 degrees divided by n. Beautiful, Qued. All right, done. So that's the proof for it. An angle, any angle here, would be n minus 2 times 180, the sum of the degrees. And since we have n many of these x's, we end up dividing that number by n to figure out what x is. All right, and I think it's a cool proof. It's a good one to look at. Now, I want to talk about one more topic, and then that'll be it. Okay, so let's talk about interior and exterior angles for shapes, and then we'll be done. So, in context, a regular polygon, so we're thinking about ourselves, let's think about a triangle here. This is a regular polygon, and just to be safe, we're going to put angles around it, so we're given some regular polygon. It's a trigon. The number of edges of this shape, we see 1, 2, 3, so it's just 3. The number of vertices, here, I'm going to write it like this. And again, so you're filling out a chart like this on a worksheet, but number of edges of this shape would be 3. Number of vertices. How many points do we have here? We have 1, 2, 3, so there are 3. Number of interior angles. Clearly, it's equal to the number of vertices. You count 1, 2, 3 angles. All right. So those are those answers right there. The sum of interior angles is equal to n minus 2. So we go 1, 2, 3 minus 2 times 180, which is, in other words, clearly equal to 180 degrees. So that's how we figure out the sum of interior angles of a triangle. The measure of an interior angle of a single interior angle is obviously going to be 60 here. We take 180 and we divide it by n. So this will give us, here we have 3, so it's going to be 3 would be n, so 180 divided by 3 will give us 60. So it's 60 degrees. Clearly, that's true right there. Okay. Now, a lot of people are wondering, how do I figure out the measure of an exterior angle of the shape? Now, there's different ways of doing it. One way is you take exterior angle. An exterior angle, the theorem that you actually can do is that you know the sum of exterior angles of any polygon is going to be 360. And since all of the angles are going to be the same, you're going to have n angles. So you're going to just write 360. And just like the other proof we did before, you just take 360. And since that would be x plus x plus x plus x, all those angles, they add up to 360. And you can divide it by n here. Now, so that would be 360 divided by 1, 2, 3. So that would be 120. Now, the way that I did it, and the way that just comes automatic to me, is that you see that this side length, you see that you know that this is going to be 60. An exterior angle, in this case, is just going to be, if we make our angle right here, do not draw it up there. Don't draw an exterior angle like that. It's a line, so you're just extending it. The exterior angle of a triangle would be 180 minus 60, which would be 120 degrees. There is a fancy formula for it. You can use the fancy formula, or you could just take 180 minus the measure of the interior angle, because you know that those are going to form a linear pair, okay? So continue, you know, reviewing these with other shapes. You know, there are quadrilaterals, and continue with that. I hope this lesson helped. If you have any questions, let me know, okay? All right, have a good day.